All right, hello Year 10s. Just making a video here with the intent of supporting your learning while you're at home. This maths that we're doing this week is new content, so it's a little bit hard to wrap your head around kind of like on your own at home. So I just made a video kind of explaining some of the main ideas, and I'll go through an example here or there. If this video lasts too long, I'll just make a few videos instead of one gigantic video. All right. So with the work that you've been given, I've got some key ideas here on this page. These are the key ideas for today's lesson, and we'll go through these examples together, and then there are questions for you to do independently. And if you get stuck, let me know, and I'll just help out where I can. Okay, so today's topic is around sketching parabolas. Now, parabola is the shape that a quadratic equation takes. So it's the happy face and the sad face, all right? But we're going to be using transformations. A transformation is any kind of change that can occur to a parabola. So a parabola can move in any direction, or the parabola can change shape, so go wider, or it can go narrower. And we can look at how those transformations occur. So here are the key ideas, and what we're going to do, instead of just reading all of the key ideas in one go, we'll look at some example questions, because parabolas can have different looking quadratic functions, and one of them is this particular function here, y equals ax squared. Another one is this one. All right, so there's actually quite a few, and even this one as well. Okay, so let's look at individual cases first, but there are key ideas for all of them. So all the different types of functions that we're going to be looking at today, they all have a turning point, so a point at which the function starts to change or change direction. So right here is the turning point, the axis of symmetry, which is where along the x-axis do you find, or even the y-axis for some functions, but for a general parabolic shape like this one, where along the x-axis do you find the axis of symmetry, so the left being equal to the right, and it's right here. So x equals 3 would be the axis of symmetry. Okay, so let's keep going. And then, of course, the y-intercepts. So that's where does this line touch and cross through the y-axis, and it's right there. That's the y-intercept. And like the key idea says in a moment, I'll show you, it's found where x equals 0, all right? And that's why it says substitute x equals 0. Because if you, for any equation that you're given, if you substitute x for 0, you'll find where the y-intercept is. All right, so they're the main ideas for all of the functions we're looking at. So let's go ahead and look at example 1, which is y equals 3x squared. And that takes the shape of the general y equals ax squared, where a can be any number. And in this specific example, it's 3. So having a look, we're looking now at the key ideas for this section here. All right. So let's go ahead and just go to Desmos real quick, and we'll graph the example. So of y equals 3x squared, Desmos. All right. So y equals 3x squared is that one right here. Okay. And here is y equals x squared, which is just our standard equation for this form. And so you can see when we put 3 in front in the a position, it got narrower. So let's see what happens when you do y equals 4x squared. What about y equals 5x squared? So you can see the larger the number gets, the narrower the shape is, all right? What about if we start doing something else where we go y equals not 1x squared, let's go 0.5, so a half x squared. You can see now it's actually getting wider. What about if we go y equals 0.1 x squared, getting really wide now, really wide. And now what if we do y equals negative x squared? As soon as we put a negative in, as discussed in class, we go from happy faces or, positive functions or graphs, and now we have a downwards or negative graph instead. We got kind of like that sad face. So it's that idea that if you put a negative on the front, you immediately reflect, and this is the idea here, you're reflecting the graph about the x-axis. So it kind of like flips across or flips over. So let's have a look at those key ideas. Right here. So if we just quickly draw y equals ax squared, let's go blue. That was just y equals x squared, right? So for this particular curve, the turning point is 0, 0. And no matter what curve you do, even if you do y equals, what was that one? When it gets wider, it becomes y equals 0.5 squared, or x squared. It doesn't really matter. Even if you do something else like this one here where it gets narrower. So maybe that's y equals 2x squared. So for either one, the turning point is always 0, 0. Yep, right there. The y-intercept and the x-intercept are both 0. So again, look at that. Both or all three of these pass the y-intercept at 0, and they pass the x-intercept at 0 as well. All three have an axis of symmetry at x equals 0 because that's the point at which the left is the same as the right. And now we've got these last couple of points here. When a is larger than 0, so for example, this case here, y equals 2x squared, the parabola is upright, and same with this example here, and same with this example here. In fact, all values, that's a 1 there, isn't it? All values in these three examples are larger than 0, therefore the parabola is upright. Now, in the case we described before, when a is less than 0, like a negative, so let's try, let's go pink, like that. That would be y equals negative, and it looks more like the green shape, doesn't it? It's nice and wide like the green one, so that would be negative 0.5x squared, roughly. And so in that last dot point, when a is less than 0, so negative, the parabola is inverted, so it goes down instead of up, all right? So that's the key ideas for those types of functions when they take this particular shape, y equals something x squared. Let's go ahead now and work on an example. So example A, sketch the graphs of the following quadratic relations, labeling the turning point and the y-intercept. So just looking at this function here, I know it takes the shape of y equals ax squared. And so we automatically know all of those key ideas that are explained before. So y equals 3x squared is upright, so it's a happy function. It's narrower than y equals x squared. Remember we said that key idea. The turning point and the y-intercept are at the origin because it's taking that same shape as y equals ax squared. And so all we're going to do is substitute x equals 1 to label a second point. So let's go ahead and do that. So for y equals 3x squared, when x equals 1, we're going to substitute 1 in for x, like that. And so 1 squared is just 1 times 1, that's 1. And so 1 times 3 is 3. So y equals 3 when x equals 1. Now, why did we do this? Well, the reason why is because it's now going to help us form the width of the shape that 3x squared makes. If you just sub in any particular coordinate, and you could have done when x equals 2 here, you're just trying to decide how wide is your function on the graph. And so now that we have a particular coordinate, we can go ahead and draw it up. So you just need 1, that's the basics. So let's go ahead and do this. I'll just make it nice and straight, like this. Draw my arrows, make sure I label my x and y axes. And so what I know automatically is that it's upright, the turning point, the y-intercept, the x-intercept are all at the origin. And so the only really thing that I need to do is put this coordinate that I found when x equals 1, y equals 3. So I'm just going to roughly estimate. So there's x equals 1, there's y equals 3. So the coordinate will be around there, like that, just estimating. And then I'll just draw in the shape that I think it is. And so it might take you a couple of goes. I'm a bit lucky with my iPad. I can just kind of go like this. And I'm not happy with that because it didn't quite pass through the origin, didn't it? So I'll take another go and I might draw from the other side. So roughly like this. And then I'll draw some arrows to indicate that this line will in fact go on forever. And that's how we do it. So by understanding those key ideas, we understand that this line will pass through the origin, and then you just find one other coordinate, which in this case was 1, 3, by substituting 1 into the function, and then you can draw the shape. So that's the example. I think this video has gone on for long enough, so what I'll do is I'll make another video explaining the second type of function that we're going to get. All right, thanks, bye.